Welcome back, Geos406 students. So for this homework module for this week, this is number 3, you are going to get some practice with porosity and permeability relationships from volcanic rocks as a proxy for how to figure out what the gas contents of magmas were in the conduit of a volcano before and during eruptions, and how gas can escape from a magma. And you're going to be applying this to the 2008 eruption of Okmok volcano in Alaska using data collected from samples from that eruption. Okay, so for background material, gas exsolution and degassing from volcanoes is really important because it largely determines things like eruption style. It also determines any gas escape you might see from a quiet volcano that's not erupting. We call passive degassing. Gas is really one of the fundamental important concepts to understand for volcanology in many ways. It tells us a lot about the composition of magmas. It tells us about how volcanoes can erupt explosively versus effusively, and it also has abundant other connections to things like hydrothermal fluids, ore deposits, and so on. So magmas sitting in a crust underneath a volcano can degas passively, which means that they give off gas coming from that magma when it's stored beneath a volcano. And I have a picture here of Augustine volcano from Michelle Coombs, and you can see that there's some steam coming out of Augustine, and then there's this bluish cloud coming out, going down the flanks of the volcano. That's SO2 gas that was passively degassing from Augustine volcano in the months leading up to the 2006 eruption. So from that gas release, we knew that there was magma stored underneath Augustine, although at this time the picture was taken, it was just coming out. It wasn't connected to explosive activity just yet, although that happened in the weeks following when this picture was taken. So the rate at which a gas can escape from the magma, balanced against how fast the magma is rising to the surface, can tell you a lot about whether the volcano is going to erupt explosively or effusively. So if the gas cannot escape from the magma fast enough as the magma rises, you build up big gas overpressures in the conduit, and that can lead to really violent eruptions, so Plinian-style eruptions or Vulcanian-style explosive eruptions. If the gas can escape easily and quickly before the magma rises up to the surface, or the magma is rising really slowly, you tend to have effusive eruptions result. So lava flows, lava domes can result. So this results in much different hazards to people living downwind or on the flanks of a volcano. If the gas escape is rapid and the volcano erupts effusively, the hazards are different. They're much less acute than if you have magma rising quickly and the gas cannot escape efficiently, and you lead to an explosive eruption with ashfall and pyroclastic flows. So the rate at which gas can escape from a magma and the gas content of that magma are really important concepts to understand and to be able to learn how to work with models for any physical volcanology class or your future career as a volcanologist. So first we need to go through some definitions. The first is porosity or vesicularity. So the porosity of a magma is basically the percent by volume of vesicles you have, or gas bubbles you have, in your magma. And when you have an explosive eruption and that magma fragments and forms pumice, and the pumice is full of holes, like shown in this picture here on the lower left, you can see holes in these samples from the 2009 eruption of Redoubt volcano, which was highly explosive. Those vesicles in that pumice represent fossil bubbles that were once gas bubbles present in that foamy magma before it erupted. So as we saw from the last slide, the difference between explosive and effusive or even passive degassing from magma from underneath a volcano, it depends upon the rate of ascent of magma, and it also is linked with the porosity of that magma and its permeability, or how easily that gas can escape. So you build up gas bubbles as magma rises to the surface and the gas exsolves into those bubbles, forming a foamy magma. Once the magma can become permeable, the volcano can literally lose steam, which means that all of that gas can escape out of permeable networks that run through the magma. So we can't really actually go down and sample magma directly from the conduit. If we could, then that would be pretty revolutionary. We'd know a lot more about volcanoes than we currently do. But we can't do that. So all we have are samples of volcanic rocks from eruptions, and we can look at those samples to basically get clues about the dynamics of magma ascent, degassing, and eruption. So again, if we go back to this pumice, you can see that it's full of holes. We call those vesicles. When the pumice is quenched and turns into a volcanic rock, the vesicles represent the gas that was once present in that magma as it rose to the surface and fragmented during an explosive eruption. So if you have that sample, I'm going to show you a cartoon here. That sample is composed of vesicles and then the dense rock portion. If we imagine that that is actually what it looked like when it was a magma that fragmented in the conduit as it rose to the surface, you can then use this cartoon to say, okay, those vesicles represent the gas bubbles that were present in the magma, and the red stuff around it, that's the dense rock part of the magma. So that's all of the molten rock part and crystals. So gas bubbles separated out from the dense rock part of that magma. If you could pull those out, you might have as much as 60% by volume to 75 to even 80 to 90% by volume vesicles in that sample. That represents 60 plus volume percent of gas stored in that magma when it fragmented. The rest is the dense magma part. So in my cartoon example here, there's 60% by volume gas represented by the vesicles. You have 40% by volume remainder, which is the dense magma part. So porosity and vesicularity are really synonymous. Porosity just means the percent of that magma that was pore space filled with gas. All right, so we're going to make some assumptions here. If you have pumice, like is shown in this picture from Redoubt Volcano by Chris Nye, and that pumice is full of holes, you can say, all right, we're going to assume that those holes, those vesicles, represent fossil gas bubbles. Those represent the amount of gas the magma had in it when it fragmented and formed that pumice. Then we can take the porosity that we measure from volcanic rocks and use it as a proxy to tell us how much gas that magma had in it at the point at which it erupted explosively and fragmented into the pumice. So we know from prior lectures that if you have a conduit, I'm showing you my conduit cartoon here. The red stuff is the molten liquidy part of the magma. The blue are vesicles. They're gas bubbles, so that would be gas bubbles in the magma. Way down deep in the crust, so we're going to call it, 4+ kilometers deep in the crust when the magma just starts to rise from the magma chamber. The bulk density is high, right? Because most of the magma is composed of the dense part, the liquid rock and crystals. You have only a very few numbers of gas bubbles here, so the gas volume percent is low, right? So you only have a few gas bubbles, they're pretty small. So the bulk density of this whole thing, meaning the dense rock part plus the vesicle or the gas bubble part, is going to be pretty high. As that magma rises, we're going to go up here through the conduit towards the surface of the earth. You can see that the gas bubbles are expanding because they're growing. That means that they're taking up more of the volume of that magma, and their dense part of that magma is much lower in terms of its proportion by volume. So up towards the surface of the earth, the bulk density of that magma is low because you have a much greater proportion of gas volume in your magma. Its porosity is really high. So you have more volume of gas and you have less volume of the dense part, so its bulk density is then low. So magma bulk density decreases as the magma ascends and starts to vesiculate. So again, one way to estimate magma porosity is by taking these erupted volcanic rock samples and estimating their bulk density. So you can say, all right, these frozen pieces of pumice, they formed at fragmentation, they were in the conduit, the pore spaces in those pummices represent the amount of gas that used to be in that magma. So if we can measure the bulk density of that rock, we know basically how much gas it had in it by volume. We know its porosity. We have to make some assumptions here though. So this assumes that when the magma rises and it reaches fragmentation, it splits apart and forms these pumices, and then nothing happens to those after that. They come out of the volcano, they land on the ground, and they represent a perfect sample of the magma, the foamy magma, and the amount of gas it had in it when it fragmented. So we're making a big assumption here that those pumices were unmodified from what they were at the moment of fragmentation when they were magma. This is a big assumption. It's not always a correct assumption. It's not always a good assumption. So how do you take a foamy magma and then fragment it and then get rid of the gas? Well, this is where permeability comes in. So as your magma rises up, I have my cartoon conduit here. You start off deep in the crust, bubbles start to nucleate, they start to grow and expand, the bulk density of your magma drops. When you get to the point of fragmentation, that's when the magma splits itself apart and you have a large volume of gas carrying fragmented magma bits out of the conduit. So this is separation of the gas from the magma at fragmentation during an explosive eruption. So you might want to think, okay, well, how actually do we measure that process from a volcanic rock? Well, permeability is one way to do that. So I have another cartoon here on the left showing, the small volume of gas bubbles way deep down in the conduit, and the arrow points up towards the surface. When those bubbles start to expand and grow, they'll get so big that they'll impinge on one another, so they connect together. And when that happens, the little film in between those bubbles will pop and open, so you get a little pore pathway. You get a little pathway in between those bubbles as they connect up. If you can connect up enough of those bubbles into one big long bubble chain or a bubble network that spans the length of the conduit and the magma, the gas actually can escape out through those bubble pathways. At that point, the magma becomes permeable. So it becomes permeable to gas transport. And this happens, we think, when vesicularity or porosity of the magma reaches about 75% by volume. But that's a very controversial number, and you'll see that there's a lot of different sort of connectivity porosities. We call it connected porosity when the magma becomes connected to permeable gas flow. You'll see a lot of different estimates for that depending upon magma composition, how many crystals you might have in your magma, and so on. So bubble coalescence leads to permeability and degassing pathways. So when bubbles connect together and form pathways for magma ascent, the magma becomes permeable. And if you have this happening when magma is rising really slowly, you might actually get rid of all the gas. The volcano basically loses steam before it can build up big overpressures and explode. Permeability describes the connectivity of gas bubbles, and it provides a measure of how easily the gas can actually flow through that foamy magma. If you can get gas escape to go easily during permeability development, when the magma becomes permeable, then it reduces the likelihood of an explosive eruption. But if you don't quite get to this state before the bubbles build up big overpressures, then you can have a simultaneous outgassing explosively, where the magma becomes wholesale permeable because it's basically blown itself apart. The critical porosity of a volcanic rock or a magma is the volume fraction of bubbles, so the percent vesicularity or percent porosity, at which that magma becomes permeable and the gas can escape. So this is a really important number. We really want to know what the critical porosity is, because if it's really high, that means that magmas can reach the surface largely undegassed and they're more likely to explode. But if that critical porosity is a small number, so maybe 30% instead of 75%, then maybe the magma can degas more easily over a longer period of time in the conduit, and more likely the eruption might be effusive, not explosive. So during explosive eruptions, the critical porosity is also likely the amount of gas the magma had in it when that magma fragments. Permeability. Okay, So this is something that if you've had Geos 101 at UAF, or you have taken a geosciences or hydrology class elsewhere where you covered fluid flow through granular media, you probably have encountered Darcy's law. So Darcy's law describes the permeability in terms of a pretty simple formula. It's basically the relationship between how fast fluid can flow through a pipe or a tube that's packed with granular material. So if you think of an aquifer, this would be how much groundwater can be transported through, say, a sand aquifer through time as that fluid percolates through the granular sandy media. So this is actually also how we describe permeability relationships in a magma, when the magma bubbles connect up and gas can flow through a permeable network in a magma. So Darcy's law is a pretty simple equation, and it basically is expressed as follows. You have a tube. The radius of the tube is r. The location of one end of the tube is A. The location of the downstream end of the tube is B. You have fluid flowing along a length L, and in this case, it may be flowing from A to B. So the volume flux of fluid in meters cubed per second is shown as Q. So that's the amount of water or gas you have flowing through your granular media in terms of volume per time, is equal to minus K, which is the permeability coefficient, times pi r squared, so that's area of the end of the cross section of your tube, divided by eta, which is the fluid viscosity in Pascal seconds, times P sub B minus P sub A divided by L. So P sub A is the pressure at point A, P sub B is the pressure at point B. So the difference in pressure across a length L as fluid is flowing through that tube determines the volume flux of the fluid flow, modulated by the permeability coefficient K, assuming everything else is constant. So that means that you have a constant liquid viscosity. So if you have a really high permeability, it means that your volume flux is low with time, and it means that the pressure buildup across point A to point B along your tube is big. So if you can measure the pressure difference across the tube, which is actually a pretty easy thing to do if you have some equipment, or even if you don't, you can do it by timing fluid flow driven by gravity. If you know the viscosity of your fluid, which for things like water and air is actually something that's already been measured for you, you know how long your sort of experimental tube is, you can actually calculate permeability K. So permeability is usually given units of Darcy's, which is the unit of permeability defined by Darcy's law. If you want to know what that equates in standard units, 1 millidarcy is equal to 10 to the minus 12 meters squared. So it's proportional to area. Okay, so for the 406 students, you're not going to work with Forchheimer's equation. The graduate 606 students will, but it's important to know about it for your background because Darcy's law has its limitations. So when you have a fluid flowing through a granular media, you're going to lose some energy due to viscous effects, right? So you have a viscous fluid flowing through grains, you're going to have friction on the grain walls, you're going to have friction as the fluid percolates through the connected pore spaces in that granular material. So energy loss has to be accounted for. Inertia can actually be important when you have high flow rates and turbulent flow. So this means that if your fluid flowing through your granular media is turbulent, you're going to also lose a little bit of energy due to just inertia as the fluid is swirling around, or it's following tortuous pathways. So the connected pathways are really, really, really squiggly and irregular. So empirical work within just the past 20 years has shown that Forchheimer's equation is much more appropriate for volcanic rocks and magma degassing. So in this case, you'd be studying how gas flows through a volcanic rock or a magma that has connected pore space in it. Forchheimer's equation is much more appropriate for that. And it's given by this equation here, where you have delta P divided by L. So delta P is that pressure difference, again, divided by the length of your experimental pathway. It's equal to mu divided by K1. So mu is the liquid viscosity times eta plus rho, which is density of your fluid, divided by K2 times nu squared. So these coefficients here are the gas volume flux is nu, and the modified pressure gradient is delta P divided by L. K sub 1 and K sub 2 are permeability coefficients. So K sub 1 is the permeability due to inertial effects, so that's Darcian permeability. And K sub 2 is actually the inertial permeability, or the viscous permeability. And that one is much less well understood in terms of its meaning for volcanic rocks and magmas, but K sub 1 is basically the Darcian permeability. So we use that usually for modeling magmas and volcanic rocks. All right, so back again to our look at volcanic rocks as a proxy for magma gas content and magma permeabilities. What we're basically looking at here is, again, deep down in the crust, you have your magma. It's just starting to degas, so you have small gas bubbles. The gas volume fraction is low, so your bulk density is high. As that magma rises up to the surface and those gas bubbles start to grow and expand, eventually they're going to start to run into each other. And when that happens, they're going to connect up and form a network of pathways through which gas can flow out of the magma. So the gas is coming from the dense part of the magma and exsolving into bubbles, and when these permeable networks form, the gas basically can go from the magma into the permeable network and then completely escape the conduit. So up here, your bulk density is low, your gas volume percentage is high, or your porosity is high, and permeability develops once those bubbles can connect up to form that network of pore space through which the gas can flow out. So again, we step over, high porosity leads to coalescence, and when that happens and these bubbles connect up and completely connect up to the margins of the magma, you create a situation where the magma basically, you can think of it as, kind of splits apart a little bit, and you have permeable pathways through which the gas can flow. At this point is when that magma becomes permeable and starts to degas. So you can measure permeability and porosity in volcanic rocks and use this as a proxy for what the magmas were doing in terms of their gas content and degassing, assuming the pumice is preserve the gas content at fragmentation. So essentially you're assuming that these pumice chunks shown in this photo down here basically represent how much gas the magma had in it when it fragmented and erupted those pumices, and then they cooled and they preserved that record of what the magma gas content was at fragmentation. So we can also measure permeability from these rock samples, and we can assume that that permeability is what that magma had in terms of its ability to degas at the point at which it fragmented and created those pumices. So we're basically using the pumices as a fossil record for the porosity and permeability of the magma at the point at which it fragmented. So permeability is usually measured or plotted and compared with the measured percent porosity, which is given the symbol phi, and I've got a little typo in here. So you're going to imagine that this F is a phi. So it's otherwise known as the vesicularity and volume percent. So the vesicularity and permeability of these pumices can be put on a plot compared to each other to examine magma degassing pathways. So it gives an estimation of how permeability develops in a magma and how much gas is needed for that magma to become permeable and allow it to degas in the conduit. So these relationships are typically shown like the graphs I have up here on the top. These are from Rust and Cashman, 2011. We have log of the permeability in meters squared. It's a log scale because you'll see permeability is a very, very small number. And in volcanic rocks, it varies by orders of magnitude as a function of the porosity or the percent vesicles. A typical plot looks like this, where you have phi plotted against permeability. the percent porosity of your volcanic rocks. So in this plot here, you can see a bunch of different symbols. The black symbols are from a paper by Saar and Manga. These are basaltic scoria from a Strombolian eruption. They have a nice, relationship. They show increasing permeability as a function of increasing porosity or vesicularity. You have some others from experiments shown by these triangles. They have a similar relationship, although it's much steeper. So where these curves dive down and hit the bottom axis or the low permeability side of the curve, this is where we estimate what that critical porosity was. So the porosity at which the magmas actually developed some measurable permeability. So in this case, percolation or permeability, critical porosity, for these basaltic scoria is around 30 to 40% by volume, whereas for these experiments up here, it's much greater. It's around 70% by volume, 65 to 70%. So if we step over to the right, we have a very similar plot, but we're looking at some different compositions of samples in magma. These are rhyolites. So these are from very explosive eruptions, whereas the ones on the left are from really pretty low intensity Strombolian eruptions, or even just some experiments on very low viscosity magmas. The right plot, you can see some open circles and some triangles here. The open circles are from a highly explosive Plinian eruption, and you can see that they're very permeable. These pummices, high permeability, and very high vesicularities or porosities. So what this means is we think that in a very explosive eruption, the magma expands greatly and it develops really high porosities, and then it becomes permeable pretty much at the moment it fragments. So the gas overpressures, and bubbles connect up and basically split that magma apart. So the critical porosity in this case would be pretty high, probably around 70 to 75% by volume vesicles. The experiments shown here, the little triangles, these show, these are actually lab experiments done to try to recreate this process and measure permeability by steps. And they show that when you have a magma like a rhyolite that's more likely to have a very highly explosive eruption, they probably become permeable at very high percentages of gas. So I know this is a little complicated, but the things that I just want you to remember here is that the permeabilities you can measure from volcanic rocks gives us an idea of the state of the magma when it fragmented, how much gas it had in it. Rhyolite magmas, these high viscosity magmas that are more likely to be involved in very explosive Plinian eruptions, those tend to have a lot of gas in them at the moment they become permeable. And we think that this is important for explaining why these eruptions are so explosive, because they started with a lot of gas and they reached very high volumes of gas, very big gas overpressures at the point at which they exploded and then became permeable. All right, so you can measure permeability in the lab, and that's a really important thing to do. You can measure it from experiments that you create. You can measure it from actual natural volcanic rock samples. Those give you an idea of what the permeability of the magma was in the conduit when it started to degas, out of whatever porosity is preserved in the pumices. But you can also model permeability. You can actually calculate it. So one of the ways you can calculate it is called percolation theory. And a paper by Saar and Manga in 1999, they took some basaltic scoria samples from Strombolian eruptions from a cinder cone, and they made all these measurements shown on this upper left graph here for the solidly colored circles. These are permeability versus porosity, and you can see they got a nice curve here. And then they fit this percolation theory model through that to figure out what the porosity was when those scorias became permeable and when that magma became permeable and lost its gas. So the percolation theory equation is given here, where K is permeability, again in meters squared. So I have a little typo here on it should be meters squared, not meters to the -2, is equal to a constant times phi minus phi critical, or phi sub CR, to the B exponent. So phi is your sample porosity that you measured. Phi critical is some assumed critical porosity at which that sample became permeable when it was a magma. And B is an exponent that you can fit. So basically what you want to do is you want to play around with different critical porosities, different constants, and different exponents until you can get a match between your observed sample porosity and a permeability curve that fits through it really nicely, as shown here in this plot. So you see these curves here from percolation theory fit through those solid circle scoria data very nicely. So you're going to use percolation theory in this lab after you've estimated porosity of a bunch of volcanic rock samples to calculate their permeabilities and then figure out what the permeability of the magma was when those samples were just before they fragmented during the explosive eruption.